Thank you very much for coming. First, I'd like to talk about tsunami and earthquake hazard because this uh, area is very close to the Cascadia subduction zone. So you're not facing just the tsunami threat, but you're also facing earthquake threat. In earthquake threat, in some cases, will be even bigger than tsunami threat. So my title will be Earthquake and Tsunami Hazards. And I'd like to thank my first author, Dr. Awater from U.S. Geological Survey and University of Washington. Today he can't be here. He's being a grandfather. He's watching his grandkid. He just retired, so but he's very important because he's the one who pointed us to that the Cascadia subduction zone is very dangerous. Before him, everybody didn't really understand how dangerous we're sitting on a time bomb here. And I work in the National Tsunami Center, so I will incorporate a lot of Dr. Awater's slide in my talk. And his data come from mostly from geological point of view, historical data. And I would talk about my look at this information from a geophysical point of view. That means it's what's going on right now, or what's going on with the past history last, say, 20, 30, 40 years. And this is the book that Awater wrote, and the title is Orphan Tsunami of 1700. This is very famous because this is a tsunami that is well recorded in Japan, but they have no associated with earthquake to this tsunami. So Dr. Awater and some Japanese colleagues are the ones who figured out this tsunami actually is caused by Cascadia earthquake, and take about 10 hours travel to Japan. So they wrote this book. It's like a breakthrough to figure out where the cause of this earthquake. And here's are the dates, some data. Here's our calendar. And, oh, sorry. I can use this one, right? Okay, here, this is our calendar. The date was 1700 in January 26th. And in the old Japanese calendar, they use a lunar calendar. It's a December 8th. And usually, sorry. Sorry. And the lunar calendar usually is about a month behind the solar calendar, at least a month. Here's a map of the old Japanese map showing the inundation area where the tsunami came in. And this is not to the scale, not like Western maps. This is just basically a drawing of a roughly like you draw some street map for your neighbors. Okay, this is the date where the tsunami came in. Here is a record. Oh, sorry. This is the record, the book of recording in here. And here are the areas where the inundation is along the Japan coast. And here is the writing in the book, and it is a Japanese reading in Japanese, but old Japanese like to use Chinese writings. So this is almost old Chinese. I can read this very well. So it tells us right at the beginning, December 9th. Remember, this is a different calendar than our calendar. And the whole thing started, investigation started with something called ghost forest. Okay, this ghost forest, the idea of ghost forest come from Dr. George Plucker, was another USGS scientist. This happens right after 1964 earthquake, and part of the forest died just south of Anchorage, and Dr. Plucker figured out why the trees died, the forest died. He called it ghost forest. During normal time, before the earthquake, the trees going pretty well. Then during the earthquake, the land will drop in that area, and the seawater comes in, and they kill the trees, and the trees die, and it's called ghost forest. Okay, it's just if you ever visit Anchorage, south of Anchorage, you see this ghost forest like this. But this happened also around here. That's where the Dr. Awater started investigation. And this, you can see the layers of sands here. Basically, you go into the area, dig out the sand, and try to figure out how old the sands are. Sorry, I just realized my voice too low. And this is how you do it. You go in there and dig in the sands, and you see how many sands there are. You date them by different methods, either by radioactive dating, or you look at microorganisms, or you look at tree rings. This is why we're digging. And this is actually very dangerous work. If you go into an area like that, all this mud, you can get sunk in there. You may not be able to get out very easily. I tried to do it myself once, just 2006. I went to the Ghost Forest in Anchorage, and I got stuck in there. I had to lose my boots, my pants to get out there. And this is the record that Dr. Awater collected for this area, Cascadia area. And the time is right now is about 2000. And the first one he investigated, this is about 1700. This is the one that the Japanese tsunami caused by this particular earthquakes. And each one up and down is in one episode. You can see there's one earthquake, another one, another one, another one. Total 1, 2, 3, 4, 5, 6, 7. 7 of them during the last 3,500 years. That's what happened in the sand. That the sand in Cascadia area tells him, and the width of this line tells how accurate he thinks that the timing is. You can see, and the height of this tells you how big the earthquake is. You can see this is about a 9.0 earthquake. This is probably even a little bigger. So you can see during the last 3,500 years, we got about 7 of them. And this is where I work in Tsunami Warning Center in Palmer, Alaska. This is our office. Our job is to save life and properties. We got to send information out for you, timely and accurate information on tsunami warning. And by mandate, we only have 5 minutes right after the earthquake occurs to send a message out. Even the earthquake hasn't stopped rapture, we have to send information out to let you know what's going on. And this is the entire subduction zone that we're worried about for this area. And it goes from the southern, from just north part of California all the way up to Vancouver Island, in the middle of Vancouver Island. This area is about the same size as Sumatra. This is a very large area. And another thing, the bigger the area, the bigger the earthquake. So this area is prone for a big earthquake. And you can see, and the Washington is in here. Located. So this holding rupture could be as big as some of the biggest earthquakes ever happened. How could it happen? We could. This is Dr. Awater's cartoon. Okay, basically he says we could have a smaller pieces rupture at different time. We can have a very large one. If it is a very large one, it could go up to size 9 or size 9.2, maybe even a little bigger. If a smaller one, I would say this smaller one would be at least 8.5, maybe 8.7 for each one of us. That's still very large. So the possible way, I'll either rupture the whole way, even rupture half 1/3 away. But even this size, like each one some rupture is 8.5, maybe 8.7, 8.8. That would be probably the 5th biggest earthquake ever recorded. And this one it might be 9.2, even probably the 2nd biggest it's ever recorded. Okay, this is the region of Cascadia from the combination of geological and geophysical data. And Dr. Awater told us that maybe the size 9 earthquake, maybe 500 years. Remember, we have 3,500 years. We got 7 of them. So the average is about maybe 500 years. And then we have other earthquakes. This is we're recording. And the deep earthquakes, okay, what kind of deep earthquake coming out here? They're about every 50 years we can get one. They're about 7. And then crustal faults, about 7 also. And those are small. These 2, I can see them from my geophysical recording. Then Dr. Awater pointed out to us there are even bigger ones. And now the puzzle is when's going to go and how dangerous are we? So this is a very, very difficult problem to answer. You can see from here And the question is, are we sliding smoothly or stuck dangerously? If this place going down there, if it's going smoothly, then very little stream build up. It may take a longer time for us to rapture. If it's stuck dangerously, we're building up strength, it may be soon. So to answer these questions, and I was in UW on Tuesday, and what we need to do is to measure the length of this area to this area. So right now we have instruments on top of here. We don't have any instrument in the ocean side. So we're talking about putting some instrument on the ocean side. Once we put some instrument here, we can measure the distance between this instrument and that instrument, like GPS. If after 3 to 5 years, we should know one of these one, which one is correct. And we look at the entire ocean, that tsunamis occurred everywhere in the ocean, but they also occur in different ways. This could be earthquake, a volcano, or landslides. And the size of the color represent how dangerous they are. The red ones, there's more deaths, and the yellow ones are less deaths. You can see we have in the Atlantic Ocean or Caribbeans, Indian Ocean, Pacific Ocean, we all have tsunamis. But which ocean has the most dangerous? We list them out here. Now let's just remember 26 Boxing Day Sumatra earthquake. That's about 250,000 people die. That's the highest we can remember. And that's Indian Ocean. That's about 10% of the tsunami occurred there. Pacific Ocean has about 80%. Atlantic and Mediterranean has 5%. So we're sitting in the Pacific Ocean. That's what's called Ring of Fire, most dangerous area. Here is we call it area of responsibility. This is our area of responsibility. We're National Tsunami Warning Center. We're sitting in Alaska. We're in charge of the entire coastline of North America. So anywhere in North America there's a tsunami threat, we're responsible. PTWC, our sister station in Hawaii, they're in charge of the Pacific Ocean, and they call the tsunami warning for American territories like Hawaii and Guam and Samoa. And then they add as advisory to other countries in the Pacific Ocean. They tell them if the tsunami is coming, they should do something about it. And Japan watching their territory on the Northwest Pacific. Then after the 2004 Boxing Day tsunami, then German helped Indonesia set up a regional tsunami warning center there. And Australia and New Zealand have their own tsunami warning center. India get their tsunami warning center because they don't get along with anybody, so they have their own. And then the French has a tsunami warning center in Tahiti, and Chile set up their own tsunami center along Chile coast. And Russia has a tsunami warning center, but they don't have any money, so they take our messages, rebroadcast. The word tsunami is a Japanese word, means harbor wave. And again, I'm lucky here. The word in writing is a Chinese character, so I can read it. And the reason it's called harbor wave, because it's Japanese fishermen will go out, their village go to high sea to fish. They're usually safe. Many times they come back home to their village. The village is destroyed in the harbor. So they figure it must be something in the harbor that destroyed their village. So they call it harbor wave. And that tells you that tsunami is pretty dangerous in the harbor, but actually very safe in the deep ocean. Okay, here let's talk about what causes tsunami. And the number one source is shallow underwater earthquakes. And at least some of the biggest ones, Chile and Alaska, Sumatra, and Japan. Those are 4 biggest recorded earthquakes. They're not the biggest earthquake will ever happen. That's just 4 biggest we recorded with the instrument. And then landslide can cause tsunami. And many times the landslide is produced by earthquake. Like in 1958, Latour Bay in Alaska, there was an earthquake caused a landslide. The water went up to about 1,700 feet. So that's the highest tsunami. So if something happened here, if a bigger Cascadia earthquake goes, you could have many local landslides. The local landslide could cause pretty high tsunami, but they're just localized. So it depends on the terrain here. You may have associated the landslide tsunami. And then, also in 1929, Grand Bank in Canada, there was a big landslide tsunami caused by earthquakes. And the volcanic eruptions, we know volcanic can cause eruption, but this is you can see over the years, there are many ways of, many big volcanic eruption cause tsunami, a lot of deaths. And this is the one thing that we try to monitor, but it's very difficult to monitor. So when volcano erupt, we will know volcano erupt, but we just don't know how much how much underwater it is. So there's no way we can determine the size of the landslide or size of the eruption. So that becomes a difficult problem. The first two we can monitor earthquake. If we monitor earthquake that's close to some very steep mountains, we can say there may be a landslide occurring. So these are two things we're doing here in our center. And then the other ways of causing tsunami, asteroid impact is some asteroid or meteorite coming from outer space, and they could cause big tsunami. And we think the dinosaur is died from the meteor coming in. And what happened is the dinosaur, when it came in and splashed into the ocean, actually splashed into Mexico 65 million years ago. And the dust went up the sky, covered the sky for 3 years. No vegetation can grow. All the dinosaurs just starved to death. And methane hydrate is another thing we worry. I'm not sure how big a threat is. 7,000 years ago, something happened in the coast of Norway. It triggered a huge tsunami. Methane hydrate as a solids like methane in the ocean, in the seabed. If the water in the ocean warms up, it could change from solid to gas, and it cause a much bigger change in volume and cause a big tsunami. So those tools are unknowns that we can't monitor, but we can monitor earthquakes and associated with landslides. So that's why we study earthquakes in tsunami warning centers. In the tsunami warning center, we identify where the most dangerous area. And this area here, the blue area, also this coastal area, the brown area in Chile, we identify as the most dangerous area in the world for very large earthquakes. And there's some other areas. Yeah.
Chile and us?
Chile, yeah, Chile, the south of Chile here. And then the rest of Alaska, there's Cascadia here, and Alaska Trench in Kure Island in Japan, the Philippines, and Tongass. This is the most dangerous area, including Sumatra here. Okay, so that's why we study earthquakes. And here, one thing I want to talk to you about, remember we talked about ghost forests. And this is another thing, we may face a danger during the tsunami that we're not sure we understand. If the plate is moving, the oceanic plate is always denser than the continental plate will move under. So in this case, the Cascadia, the one Fuca plate will move under, coast of west coast of America, and if it gets stuck, like I told you earlier, and part of the plate, the front, ocean front will be dragging down, the land side will come up, and this will take the time of about a few hundred years, the average time of set up earthquake. When earthquake happens, in a few minutes, the front that dragged down during the 500 years or so will snap up, and the back will come down. This is what, if you're sitting here, then you could have a land come down. That's where the ghost force occur. So this is Dr. Placker's study for Alaska earthquake. The beginning idea, we can see the front, the ocean front came up during the earthquake. The land side goes down. And this is just a whole bunch of data pointing the ocean front comes up, the land goes down. And the same thing again. That basically point out, if Cascadia happened today, part of the Oregon coast or Washington coast could go down instantaneously for 2 or 3 meters, about 6 feet, and the water will come in right away. And if tsunami is different kind of, remember, let me explain to you why tsunami is safe in the ocean but it's not safe in the harbor. Let's say I have a boat sitting here, and if I'm in a deep ocean, tsunami will go underneath me, and the wavelengths are very long, and it takes a long time to go. That means like if I have a boat sitting here, I'm sitting on top of the boat, the tsunami go underneath me in the deep ocean, will lift up the boat like 2-3 meters, and will drop the boat back. It takes about half an hour to go up and down because the motion is so slow. You don't feel anything. You're pretty safe. But when the tsunami comes to the harbor, it's like a whole train pushing. The front, the engine puts on brake. The back doesn't know. So the back train keep pushing. Your distance gets smaller. So wave gets shorter. And you can see this is deep ocean. You have very long wavelengths. You have very little uplift. It takes a long time to go this. When you get to near the harbor, the distance gets smaller between waves, and the wave height gets higher. That's why tsunami gets very dangerous in the harbor. And tsunami also travels at a very fast speed. This is a tsunami speed. It's very easy to calculate. It's just gravity constant. We know that that's a constant. And depths of ocean, this is depths of ocean. Since we know how deep the ocean is, anywhere in the ocean, we can calculate when tsunami get to you, if an earthquake happen, and can see, depends on the ocean depths. This is 4,000 here. It's the average depth of ocean. And here, that speed is travel more than 200 miles per hour. But when deeper ocean can go even faster, okay? So tsunami can travel at the speed of a jet airplane. So remember Japan even occur. If somebody jump on the airplane in Japan, when earthquake occur, the tsunami will get here probably before the wave gets here. And this is one up. We see some of the people here calculation, especially the natural resource people, they calculate run up. So basically, it's calculate how much water is being pushed. Say, assume this is the beach. We want to calculate how much inside, how high it goes, how deep it goes. This is called run ups. And this is very dangerous. So that's why we have tsunami evacuation maps. Okay, tsunami propagation. Now let's talk about tsunami. It's most devastating near the earthquake. Since we know this area, earthquake is just offshore. It's pretty close along the Pacific Ocean. And so this area, we're not only facing tsunami danger, we're also facing large earthquakes. We're talking about size of earthquake about 9 or so. That is devastating. The earthquake could probably cause even more danger than tsunami here. And let's talk about the wave. How much wave is it? If we are in the watching people surfing in Hawaii, you can see people coming over. The wave is very high, tumbling over. It looks very dangerous. But the wave length between the one wave to the other one, you can see one wave, you see the other wave. You can tell the distance between them. You take that, put it sideways. That's how much water is moving. So, for example, if it's 300, 600 feet between one wave to the other wave, you turn it sideways, so that means only top 300 feet is moving. Below that, the ocean is not moving. So one wave is only top few hundred feet are moving. Tsunami waves are very long, so that hundreds of kilometers or miles, hundreds of miles long. So you can see the ocean is only 4 kilometers deep. You turn it sideways, this is much bigger than 4 kilometers. So that means the entire ocean is moving. And the motion is no longer circular, it's like horizontal. So that's why tsunami comes in as a flood. And remember, this tsunami is the entire ocean is pushing. How dangerous tsunami is, I did some calculation here. And say take Japan quick. This is some information. We do the calculation, 7.5 gigawatt per kilometer, 7 megawatt per meter. You don't worry about what that means. Let me explain to you. So take a tall person in this room. You will put him on the side along the beach. He's about 2 meters tall. And that means is that he will have 15 megawatt energy hitting him, power. 3 megawatts a diesel generator. That means he lie on the beach. The 5 diesel locomotives will run over him at the same time, over back and forth. That's how powerful it is. If we take a mile of coastline and then calculate, this will be about 2 kilometers. So we get about 15 gigawatt a mile. The biggest nuclear power plant is 8.2 gigawatt. That means in a mile coastline, I have the power of the biggest power plant, 2 of them coming in that 1 mile coastline. That's how powerful it is. All the energy coming there. And turning to Hoover Dam, everybody knows how big Hoover Dam is, the biggest hydroelectric power we have here. It will take about 7 to 8 of them to equal to 1 mile coastline. That's how powerful it is. And another thing, tsunamis can travel all different directions. It's like a drum coming in, very long waves. So you can see hitting this place, tsunami can come in this direction, come from the top, from the bottom. That's why tsunamis at times, it's a whole bunch of serious wave. It just doesn't end. It keeps going on and on. And let's skip this. The bigger earthquake will cause big tsunami. The bigger one, because here, at least the 4 biggest one, and you can see they all cause huge tsunamis. We're expecting Cascadia to have something at least similar to this size here. Here is what we're doing in Tsunami Warning Center. We monitor the entire world. Each one is a seismic station. There are over 1,000 seismic stations we monitor constantly. And we have data have to come in. Anything more than 20 seconds late, we throw them out. And here are the tide gauge we monitor around the world. Over 1,000 of them too. And some of them with numbers are the tsunami gauge we have the ocean bottom. Those are confirmed if a tsunami generated or not generated. And then another thing is the longer the rupture, the more dangerous. If you felt an earthquake here for a long, long time, that means it's very likely to have a large tsunami. So the longer it goes, the more dangerous for tsunami generation. And here at least the big earthquakes around the world. Again here. Now I want to show you this diagram. I calculate, look at all the big earthquakes since 1900. Anything over 8.5. You can see if there's 8.8, 1905. Here it's very quiet. No big ones. There's total 4 big ones from 1900 to 1938. They're not very large. But from 1950 to 1965, there's 7 big ones, including the biggest one, Chile, and the second biggest one, Alaska. Then right after that, for 39 years, from 1965 to 2004, there's 0, none, no big ones. And then from 2004 until now, we have 6 big ones, bigger than, those are big, really big tsunami-generated earthquake. But I'm not sure when the biggest one is yet. So I put a Cascadia here. This is my guessing. I don't know, it could be the biggest one coming. Here's another thing I will show you. This is the data I saw in Japan quick. I was in the office about 5 minutes after the earthquake. And I saw this data come in. And I only see this part here at that time. And I saw that the one tide gauge in Japan shows about 3 meters, about 10 feet of wave coming in. I said, well, that's impossible because tsunami doesn't come in that fast. I didn't know why was that. So later on, when I saw this data, a few days later, I realized that's what happened to Japan. The line was dropping. The water was coming in because the line was dropping. So this is something could happen here during the earthquake. Line will be dropping. And here's the cartoon showing in between earthquakes, the subduction going down there, the island of Japan being pushed up, remember? And the front being dragged down, the back's being pushed up. During the earthquake, this energy release, the land relaxed, land will drop down. So during the earthquake, Japan dropped, the land dropped. And that, remember the Fukushima nuclear accident, that was, the reason was the land was dropping, land dropped down. And here shows the data of land dropping and the after earthquake, the post during the earthquake. Here's a cartoon that Dr. Awater showed. This normal time, the sea is here, we're all here, everybody is safe. Then tsunami could come in. First, the land will drop during the earthquake. It's likely land will drop. Then tsunami will come in. Oh, sorry. Eventually, we have a ghost forest because the tsunami comes over. I think this is one here, right here. The land, you can see the lands in the back here, being overwhelmed by tsunami. But land also dropped 2 meters. And this is talk about size of earthquake. We have a real way of calculating earthquake size. It's basically how hard the rock is, how much goes up and down, what the area is. So this is a very simple formula. But the data come out here is something that nobody understands. Some units nobody understands. So we convert that into something we understand, magnitude. That magnitude Richter invented. It really had no physical meaning, but we convert these two together. Now we can use Richter. We can roughly estimate how big an earthquake is, so everybody understands. And that's it. Thank you very much.
So, thank you, Paul. I wanted to. I'm sorry that we didn't have Brian Atwater. I know the first time I advertised the event that was one of our keynote speakers. But thank you, Paul, for coming all the way down from my home state of Alaska to do the presentation. Yes, thank you. Okay, we have. We'll take a couple of questions before we go into the next speaker. Okay, over here.
Well, like you drop a rock in the water. Like I drop a bucket, anything in the water, like a rock in the water, the wave goes in all directions. So you're on the coast, the tsunami happens. Some part will go hitting Japan here, but the other part will go hitting our coast because our coast is closer, so it get us first. Yes. Tsunami energy is very powerful. If you can harness it, there's a lot of energy you can use. Let me just compare some. If one earthquake, say for example, one earthquake magnitude 9, if we can harvest the energy, that would be equal to about 300 years of energy used in the entire world. That we can use that much energy if we can just harvest one of them. Yes. Yes, tsunamigenic. I think it's probably scientific making up that term. It means it could be is possible to generate tsunami. Yes.
Yeah, it looked like from the frequency that you had in terms of timing.
Yes.
The next big one, it looked like we had about a 500-year period for a 9-point. It looked like we were more right now in a 7 to 8-point period. Is that true?
Well, I'm looking on the biggest one. Remember that 500-year period is for this area only, but everywhere else could have their own periods. So.
I got that. I'm talking about where I live.
Right. Our last one was about 1700 from Dr. Awater's studies, about 1700. So.
What's that period of time? Are we talking 1700? How many years do we add to it until we're looking at another?
Yeah, on the average, it will be about 500 years, right? But the thing is, nature doesn't happen exactly on time. So it could be early, it could be late.
I got it. But right now, if you're trying to eyeball it, it looks
300 to 600 years. 500, pardon? 300 to 600 years.
3 to 6. Got it. Okay. So we're in the zone.
We're in the zone. It's possible we could have an earthquake.
One more question?
Yes.
One more question in the back over here.
Yes.
If you're out on the water on a motorboat or a kiteboard and you feel a jolt, instead of going to the land, would it be better to go straight up to the sea?
Well, if in theory, depends how fast you go. If it lands very close, you may just go on land and run away, right? If it's you're on the sea, you're far away, you might just want to drift into deep ocean. And I would suggest, during the tsunami warning, the navies and fishermen and Coast Guard will take the boat into deeper ocean. It's safer there. Yes.
Can you feel a jolt on the water, or can you only notice that gradual meter?
I don't think you can feel the jolt on water. That's why you got to keep a NOAA radio with you.
Speaking of that, thank you for that. Did everyone get a raffle ticket as you came in the doors? raffle drawing ticket that we are going to do a drawing at the end of the night for 2 NOAA weather radios. So we will do that before we adjourn for the evening. But if you did not get a ticket, there's still time. You can step right outside here and John will give you a ticket. Okay, do you want to go into the next section?
Yes, let's go to the next section. I'm just going to lead off for Ted. I'm just quickly talk about our operation in the center. This is what we do every day. This is our operation center. This is where everything begins. You can see we have many monitors, and there are 2 monitors. That means 2 people on duty all the time. We're 24-hour operations. We watch the entire coastline for you. Again, this is our AOR. We're in charge of North America, entire North America. And again, this is the same thing. We talk about different tsunami threats, and we monitor the world seismically. This is the number one thing. We monitor this constantly, and tide gauges. And on these things, everything on this screen here, all the software written by the people in-house here in Alaska. We wrote every software we did in here. And you can see we basically monitor the data coming in, and we look at long period. That tells us if there's a big one coming in. And we use it to solve the earthquake here. So this is the frequency. We look at the frequency between 1 and 100 seconds, maybe a few hundred seconds. This is the data we use. What we do is a quick magnitude calculation, location and magnitude. And from there, we estimate if it's a threat. And the way we do it, we monitor the entire world. We quickly calculate earthquake, the magnitude and location. Using historical data or guideline, we can determine our first message. Shall we go out with a message? And then after that, we use tide gauges and modeling. Go after second message or later. The first message definitely is with seismic only. After that, it could be seismic or tide gauge or modeling data. And here shows, in theory, remember, the earthquake takes time to rupture. It shows the magnitude calculation is very difficult. Depends what magnitude we try to use, different frequencies. This diagram tells us at the beginning this is impossible in theory. There's no way we can calculate magnitude. So, for example, this MB here, that means that anything, this 1 second period, anything bigger than 5, we're not sure. We cannot determine because it's not accurate. And you will look a longer period. Anything bigger than 20 seconds and anything over 7, we can't be sure. So it's a very difficult problem. And this is the formula I showed you earlier. So we convert again to magnitude. Now, this is our facing problem. We're going to make a decision in 5 minutes to send a message out. The different magnitude tell us different things. They're all wrong. And this is the final results. We can see one thing we notice, they all underestimate. We don't know how big the earthquake is. So, but this gives a way for us to solve the problem. Since we know they all underestimate. So what we do is we say, okay, we don't know what happened. We just add this back. This thing say that it's supposed to be like a 8.3 here. We only got 7.6. We know we're 0.7 off. We add it back. Okay? So that's our technique. I calculate all the biggest earthquake in the last 50 years. I go through this and the average, take an average, do a lookup table. Every time an earthquake happens, we add these things back. So this is what happened in Japan. In 5 minutes, I have 8.1. 6 minutes, I have 8.2. 8 minutes, I have 8.6. 9 minutes, I have 8.8. At this time, I called NEIC, National Earthquake Information Board. I also called PwC. I told them I have 8.8. But the entire world, everybody only has 7.9. And nobody agreed with me. Half an hour later, they call back. They say I was right. So this is how we do things. We use some empirical way to calculate, but we are always right. Okay, and this is our method. You can see over the time we get closer and closer. In 9 minutes, we get very close to the final results. And this is different ways of calculating magnitudes. And everybody in our office has to understand each one. What does it mean? And here's the results. For example, I told you we have the mandate is 5 minutes. 5 minutes we send message out. This is each one earthquake. On the average, you can see at this time, this month, on the, this period, we average about a little more than 3 minutes That's how fast we send the information out. How accurate we are. Location-wise, we're on average little more than 20 kilometers off. But remember, those quakes are very large. Some of them thousands of, few thousand kilometers long. Some are a few hundred kilometers long. So we're only 20 kilometers off. We're pretty close. And here is the magnitude. On the average, we're about 0.2 off. Remember, this is our result. Come out on the average is 3 minutes. The final result come out usually several days, maybe several years later. They'll calculate that. So we're pretty good. And then we use this. We send the information out, and Ted will get the information, and he would tell us what he does with it. And this is a different type of message. Ted will talk about our different message types. And okay, we can skip this. Basically, for local earthquakes, education is the most important. We cannot give you enough warning. Remember, the water will come in right away if the land drops. And we cannot send the information out fast enough. If you wait for us, it will take about at least 5 to 10 minutes before it gets to you. And this is how long the tsunami lasts. And that's it. I send a message out, and Ty will get it.
So yes, we received those information, the tsunami warnings from Paul in his Palmer office. We received them in my office in Jefferson County Emergency Management, and so we monitor that every day. They come across, and most of the time, and luckily, they say that there's a large earthquake and no tsunami is expected. So I like to see that. It's the first line I look for: no tsunami expected. All right, so we have a couple more speakers, but I wanted to see if there's just one or two more questions before we have yes, in the back. Pat?
Dr. Wang, it's been my understanding that when there is a tsunami generated, it's not a single wave, it's a series of waves over time. And that actually it's the second, third, maybe fourth wave that is the biggest. That it's not always the first wave that's the most damaging.
That's so, but not always the first wave. It's very complicated problem. It may be a second one or third one, maybe even later.
So how much time, if we had a large wave coming in here,
Uh-huh.
how much time would we be vulnerable to tsunamis from the first wave until the threat was gone? How much elapsed time?
Well, it really depends on terrain, also depends on the size of earthquake. For Japan, for example, along Japan coast, it will last, several hours, maybe 10 or 20 hours before Japan called off the tsunami threat. So in our coast, if something happened here, I would say if we send a message out, tsunami warning out, I wouldn't be able to call off the threat at least a day or 2 days later for that big earthquake.
So we could be looking at the risk of multiple tsunamis for up to a day or longer.
Yes.
Okay.
Yes. Yes. Yes.
Have you ever been through one?
Repeat the question.
Yes, I have never been in a tsunami, but I have went through several big tsunamis operation, and the biggest one I can remember is Japan, of course. I was there about 5 minutes after the earthquake had struck. I was there until 35 hours later to the cancel. I was there the entire time. Also, the next biggest one is Chile, 2010. I was there from beginning to end. That's a very large earthquake. It caused a large tsunami. Yes?
So I've been told that it could be within an hour or hour and a half that the tsunami wave would hit this area, Port Townsend. What? An hour? Why is it if it's going, let's say 200, slow it down to 200 miles per hour? We're only 100 miles inland. Why is it an hour? Why is it not 30 minutes?
Right. That's a good question. Tsunami speed of tsunami wave, it depends on how deep the ocean is. It travels, in this area, it gets shallower, so the wave gets slowed down. So if it's deep ocean, it gets faster, and shallow water slows down.